Hello, everyone. In this video, we're going to look at the notes and examples from section 3.2 on the Fundamental Theorem of Calculus. And we're also going to look at anti-differentiation. So that is finding functions whose derivatives are known. So let's first look at this Fundamental Theorem of Calculus. The Fundamental Theorem of Calculus relates integration to differentiation, and it states the following. So if f is a continuous function on the interval from a to b. So the picture we should be having in our head here should look something like the following. So here's a set of axes. We have a function that we'll call f of x. Well, there's no breaks in the function f, so it's continuous on some interval from a to b. Okay, so that's the setup so far. Then, if you want to compute the integral from a to b of little f of x dx, that is equal to big F of b minus big F of a, where what is this big F function? Where f of x is an antiderivative of little f. So what does that mean? I.e., derivative of big F of x with respect to x, or if you'd like, f prime of x is equal to little f of x. So let's just take a moment to pause and reflect on all that this statement is saying. So in this statement, we have a function, little f, that is continuous on this closed interval a to b. So the situation here. Then if we want to determine the area under that curve on that interval, to find that area, we just need to find an antiderivative of little f and then plug in the limits of integration, in this case a and b, into our function. We first start with b and then subtract a. So take a moment to possibly pause the video and reread this statement for yourself. Make any extra notes you'd like to, and then continue watching. One way that we can make sense of this statement is to consider the types of integrals we were looking at in the previous videos. So before, the integrals we were looking at were related to rate of change functions. So those little f's we were looking at were rates of change. And so we're adding up the rate of change over an interval. So then it might make sense that then that area under the curve, or those accumulated changes, are going to relate to an antiderivative, or the original function, if the f was our derivative. So let's look at an example of what an antiderivative is, or how we might find it. So example 9 here says, find f of x if the derivative of f is equal to 2x. So take a moment to pause the video and see if you can think of a function, a possible function for little f. All right, so one function comes to my mind, and maybe this was the one that you thought. Well, little f of x could equal x squared. And let's just check to make sure that is, in fact, consistent here. So if we take the derivative, f prime of x, we use the power rule, so we write 2x. Awesome. So that checks out. But are there any other possible functions for f? What if, instead of just x squared, we wrote x squared plus 7? Is the derivative f prime of x still equal to 2x? Well, now that first term, the derivative is 2x plus derivative of 7 is 0, so plus 0. So again, we have the derivative of this new function x squared plus 7 is also 2x. So are there two functions? Are there any more? Or, well, we could have wrote f of x could be x squared plus pi. Here again, we see the derivative f prime of x is equal to 2x. And in fact, we could have written any constant here. We could have added any constant to x squared to have a function whose derivative is 2x. So in general, when we're finding this antiderivative of a function, so in this case, f is the antiderivative of f prime, we write a plus c here. And that's just to denote that we could have, or rather that our antiderivative is going to be any function of this form, where c is just any constant. And just to recap here, f would be called the antiderivative of our function f prime. So let's look again at a definition of antiderivatives and summarize it in this box here. So an antiderivative of a function f is any function big F, we're just using different notation here, any function big F where the derivative of the big F function is equal to our original function. So in this previous example, an antiderivative would be x squared. An antiderivative of 2x would be x squared plus 7. Another antiderivative would be x squared plus pi. So often we refer to all of these antiderivatives as a family of functions. And typically, if we're being asked to talk about the antiderivative, then we do write the function using that plus c. So just to recap some of what I just said here. So we look at a family of functions. So we often write big F of x plus c. So big F is just any antiderivative, but then when we plug in or put in a plus c to indicate that we could also be adding any constant, then we look at the antiderivative, and this is called a family of functions. Okay, you won't need to worry too much about that language. But one other bit of notation I want to use is often then when we're asked to find an antiderivative of a function, rather than say it all out, what is an antiderivative of little f? We just write notation integral of f of x dx. So this is often how we notate our family of functions, big F of x plus c. And so just in language, we'd say this is the antiderivative of little f. So here it is on the left in notation, and here it is our resulting antiderivative. All right, so in the next videos, we're going to look at some examples, finding antiderivatives and computing integrals.